The universe contains trillions of planets, yet we hear only silence. That profound mystery has a potential new answer, and it begins with the beautiful dance of light in our own sky. Those shimmering northern lights are more than a spectacle. They are a symptom of a violent cosmic process, one that might be sterilizing worlds across the galaxy. This is the Aurora Effect, a compelling hypothesis that suggests the very phenomena that create auroras could be the reason complex, intelligent life is vanishingly rare. By the end of this exploration, you will understand why our existence might hinge on winning a cosmic lottery with staggeringly low odds. We will journey through the hidden dangers of the most common stars, uncover the planetary shields that protect us, and confront the possibility that most Earth-like worlds are bathed in beautiful, deadly radiation. What does our own quiet corner of space tell us about our place in the cosmos? Our cosmic silence has a name, the Fermi Paradox. It asks a simple, haunting question. If the universe is so vast and so old, brimming with countless stars and planets, then where is everybody? The numbers suggest a galaxy should be buzzing with civilizations, yet our telescopes and radio dishes hear nothing but empty static. For decades, scientists have wrestled with possible answers, often grouped under the idea of a great filter. This is a hypothetical barrier, a catastrophic step in the evolution of life so difficult that almost no world gets past it. Perhaps the filter is behind us, a near impossible step like the origin of life itself, making us miraculously early. Or perhaps it lies ahead, a grim future event like self-destruction through war or technology, waiting to silence every civilization that rises. These ideas focus on biology or sociology, on the fragility of life or the instability of intelligence. But the Aurora Effect proposes something different, a filter not of biology or choice, but of fundamental physics. It suggests the bottleneck isn't about becoming smart or building radios, it's about building a safe home in the first place. The violence of a planet's own star and the strength of the planetary shield that must withstand it could be the universal gatekeeper. This shifts the question from why don't we see aliens to why would any complex multicellular life ever get a chance to evolve at all? The silence may not mean civilizations are hiding or dying. It may mean their worlds are, and have always been, profoundly uninhabitable. The Aurora Effect is a cosmic paradox of beauty and destruction. Those shimmering curtains of green and red in our polar skies are not just a light show. They are the visible signature of a planetary shield under attack. The sun constantly ejects a stream of charged particles, a supersonic wind blowing through the solar system. When this solar wind reaches Earth, it does not hit our atmosphere directly. Instead, it slams into an invisible force field generated by the molten iron in our planet's core, our magnetic field. This magnetosphere deflects the brunt of the storm, funneling some particles toward the poles. There, they collide with gases in our upper atmosphere, exciting atoms and molecules and making them glow. That glow is the aurora. It is proof our defenses are holding, a beautiful leak in an otherwise vital barrier. Now imagine a world without that magnetic shield. The full fury of the stellar wind would strike the atmosphere head-on. Over time, this relentless bombardment could erode the air itself, molecule by molecule, stripping the planet bare, just as scientists believe happened to Mars. Even with a magnetic field, if the stellar wind is too powerful, it can compress that protective bubble, allowing radiation to reach the surface. This is the heart of the Aurora Effect hypothesis. For a planet orbiting a very active star, the auroral displays would not be rare, dancing lights near the poles. They would be global, constant, and lethal. The surface would be bathed in radiation that shatters complex molecules and mutates DNA. The atmosphere could be slowly torn away. The conditions for life to begin are one thing, but for life to evolve over billions of years into the complex, multicellular organisms we see on Earth requires planetary stability. It requires a calm, protected environment. The Aurora Effect suggests that for the most common types of stars in our galaxy, that calm is an impossible dream. The very phenomenon that paints our sky with wonder could, elsewhere, be the brush that paints a world sterile. Our existence depends on a far more specific recipe than just the right distance from a star. The classic idea of the habitable zone, that band around a sun where water can remain liquid, is often called the Goldilocks zone. It is a beautiful, powerful concept that has guided our search for alien Earths. But it is also dangerously incomplete. Think of it like this: finding a house in a neighborhood with a perfect, temperate climate means nothing if the house itself has no roof, no walls, and is sitting in the middle of an active artillery range. The Goldilocks zone gives you the climate. It does not give you the shelter. A planet needs two more critical things to harbor complex life. It needs a stable, gentle sun, and it needs powerful planetary defenses. This is where our search hits a cosmic snag. The most common stars in our galaxy, by a vast majority, are red dwarfs. Small, cool, and long-lived, these stars should, in theory, be ideal hosts for life. Their habitable zones are close and cozy, but red dwarfs have a terrifying temper. They are prone to violent, frequent tantrums in the form of massive stellar flares and coronal mass ejections. These are not like the occasional solar storms our sun produces. These are apocalyptic outbursts that can double the star's brightness in minutes and blast its orbiting planets with waves of X-rays and ultraviolet radiation, coupled with torrents of charged particles. A planet in the habitable zone of a red dwarf would be perpetually bathed in this radiation. Its atmosphere would be under constant assault, its surface scoured. It would become what scientists call an aurora factory. The entire sky might constantly shimmer with lethal, beautiful light as the planet's magnetic field, if it even has one, is overwhelmed by the stellar fury. Any tentative beginnings of life in the oceans or damp soil would be repeatedly sterilized, resetting the evolutionary clock over and over. So while our telescopes have discovered thousands of promising worlds sitting in that theoretical sweet spot for water, many of them are orbiting these tempestuous stars. They are in the right place but with the wrong sun and likely without the right shields. The Goldilocks zone, it turns out, is merely the first and easiest condition on a very long list. These tempestuous red dwarfs are the silent majority of our galaxy. For every star like our Sun, there are at least 10 of these small, dim M-dwarf stars. They burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. This incredible longevity seems at first like a gift to life. It offers an almost endless timeline for evolution to work its magic, but that gift comes with a monstrous catch. To receive enough warmth from such a faint star, a planet must huddle extraordinarily close, well within the orbit of Mercury in our own solar system. At that intimate distance, the star's gravity takes a firm, unyielding grip. The planet becomes tidally locked, with one hemisphere in permanent, scorching daylight and the other in eternal, frozen night. A thin band of twilight might exist between them, but that is not the main problem. The true danger is the star's personality. Red dwarfs are notoriously unstable in their youth for billions of years. They frequently erupt in titanic superflares, sudden explosions of energy that can make the star 100 times brighter in an instant. These are not the solar flares we occasionally experience. A single red dwarf superflare can release more energy than our Sun does in a century. Along with this flash of X-rays and ultraviolet radiation comes a coronal mass ejection, a billion-ton cloud of charged plasma hurled directly at the nearby planet. Imagine a world where, without warning, the sky erupts in a searing flash of light. The gentle red sun suddenly becomes a brilliant, deadly blue-white. In the hours that follow, a wave of high-energy particles slams into the atmosphere. For a planet without a robust magnetic field, this is a direct sterilizing blow. The radiation would shatter atmospheric molecules, potentially creating a global smog. It would scour the surface, mutating any complex chemistry and stripping away the atmosphere over eons. Even with a magnetic field, the constant bombardment from such frequent storms would compress and stress the planetary shield relentlessly. The auroras would not be confined to the poles. They would be a global phenomenon, a constant, beautiful, and lethal glow across the entire sky, a permanent symptom of a world under siege. The very stars that offer the most time for life may also be the ones that make it impossible. Our survival is a testament to a silent, invisible guardian. Deep within Earth's core, a churning ocean of molten iron generates a powerful magnetic field, a force that extends thousands of miles into space to form our magnetosphere. This is not a solid wall, but a dynamic, teardrop-shaped bubble of magnetic influence. When the supersonic stream of charged particles from the sun, the solar wind, reaches our world, it does not hit us directly. It encounters this magnetic shield. Most of those particles are deflected around the planet, flowing harmlessly past like water around a stone in a river. Some, however, are captured and funneled by the magnetic field lines toward the north and south magnetic poles. There, they spiral down into the upper atmosphere, colliding with oxygen and nitrogen molecules. The energy from these collisions is released as the shimmering, dancing lights of the Aurora Borealis and Aurora Australis. Our beautiful polar lights are, in essence, the controlled release of a cosmic storm, a sign that our planetary defenses are working perfectly. They are a pressure valve, allowing a small, harmless fraction of the solar wind's energy to dissipate in a spectacular display, while the bulk of the deadly radiation is kept at bay. This system protects not just our atmosphere from erosion, but every living thing on the surface from a constant drizzle of mutagenic particles. It is the reason our planet has maintained a stable, thick atmosphere and a temperate climate for billions of years, providing the long-term calm necessary for life to evolve from single cells into the breathtaking complexity we see today. To understand the catastrophic alternative, we need only look to our rust-colored neighbor. Mars presents a stark and sobering contrast, a real-world example of a planet that failed the test. Billions of years ago, Mars was a warmer, wetter world with rivers and lakes. It likely also had a global magnetic field generated by a molten core. But Mars is smaller than Earth and its interior cooled more quickly. When that core solidified, the planetary dynamo shut down. The magnetic shield vanished. Left utterly exposed, the Martian atmosphere was laid bare to the full force of the solar wind. Over hundreds of millions of years, that relentless stream stripped the air away, molecule by molecule, leaving behind only a thin, frigid wisp incapable of retaining heat or supporting liquid water on the surface. The once blue skies turned to the thin, cold vacuum we see today. Mars became a global desert, its potential for life extinguished not by a sudden impact but by a slow, suffocating bleed into space. It is the ultimate cautionary tale of the Aurora Effect. Without that magnetic shield, even a planet in the habitable zone can be rendered utterly lifeless. The presence of a strong, persistent magnetic field is not just a helpful feature for a living world. It appears to be an absolute necessity, a non-negotiable requirement for maintaining the stable environment complex life demands. So we are left with a profound realization. Our existence depends on a series of cosmic felicities, a stable star, a planet at the right distance, and a churning metallic heart that has not stopped beating for over 4 billion years. Our magnetic field is the first line of defense, but it is not an impenetrable wall. A fraction of the solar wind's energy always gets through, channeled toward the poles. That is why we have auroras at all. This is where the second critical layer of our planetary armor comes into play, our atmosphere itself. Earth's atmosphere is not just the air we breathe. It is a vast, deep blanket of gas, miles thick, that acts as a phenomenal shock absorber and radiation shield. When those high-energy particles funneled by the magnetic field slam into the upper atmosphere, they do not reach the ground. Instead, they collide with molecules of nitrogen and oxygen tens of miles above the surface. These collisions do two vital things. First, they rob the incoming particles of their dangerous energy, converting it into the harmless, beautiful light of the aurora. Second, they generate heat which dissipates harmlessly into space. The atmosphere takes that punch and spreads it out, neutralizing the threat long before it can touch the fragile chemistry of life on the surface. It is a brilliant passive defense system, but this system only works if the atmosphere is substantial and robust. A thin, wispy atmosphere offers little resistance. Think of it like the difference between a bulletproof vest and a t-shirt. The magnetic field deflects most of the bullets, but the ones that get through are stopped by the dense, layered vest. A planet with only a t-shirt for an atmosphere is left completely vulnerable. This brings us to a major problem for many potentially habitable worlds, especially those orbiting the common red dwarf stars. Recall that to be warm enough, these planets must huddle very close to their star, becoming tidally locked. One side faces perpetual, blistering daylight, while the other is in eternal, deep freeze. This creates a planetary-scale atmospheric crisis. On the scorching day side, the atmosphere heats up and expands violently, while on the frigid night side, it cools and contracts. This extreme temperature difference can set up catastrophic global wind patterns, or worse, cause the atmosphere itself to literally freeze out on the permanent night side, collapsing entirely. What remains is a thin, unstable blanket of air weakly bound to the planet. This is a perfect setup for a process scientists call atmospheric sputtering. When the star erupts in one of its frequent superflares, it blasts the planet with that intense wave of charged particles. Without a thick buffer, those particles hit the thin atmosphere with tremendous force, not just exciting molecules to glow, but physically knocking them right out into space. It is like sandblasting the air off the planet. Over millions of years, this relentless bombardment can strip a world bare, leaving it as dry and airless as Mars. So even if a tidally locked planet somehow generates a magnetic field, its atmosphere may be too thin, too uneven, or too weakly held to survive the stellar onslaught. The beautiful global auroras would be a sign of the atmosphere actively disintegrating. A planet needs both a strong magnetic shield and a deep, resilient atmospheric blanket to have any hope of fostering complex life. One without the other may lead only to a slow, silent death in the vacuum of space. This beautiful, deadly light is a symptom of a deeper violence. The high-energy particles that create auroras do not simply produce a harmless glow. They are wrecking balls on a molecular scale. When these charged particles, protons and electrons moving at a significant fraction of light speed, slam into a planet's atmosphere, they do not stop at making gases shine. They rip through the air, colliding with molecules and shattering them apart. This process, called ionization, creates a cascade of secondary particles and intense radiation, turning the upper atmosphere into a chemical and biological war zone. For any life attempting to gain a foothold on the surface below, this creates two catastrophic problems. First, the direct biological assault. If this particle radiation reaches the ground, it acts like a microscopic hailstorm. It tears through living tissue, breaking the delicate bonds of complex organic molecules, and most critically, shredding the long strands of DNA that carry the genetic code. A certain level of mutation is the engine of evolution, but a constant high-level bombardment raises the mutation rate to unsustainable levels. Genetic instructions become garbled, repair mechanisms are overwhelmed, and cellular machinery breaks down. Complex multicellular life, with its intricate systems and long development times, simply cannot stabilize under such conditions. Only the simplest, hardiest single-celled organisms, perhaps buried deep in rock or ocean sediment, might survive by sheer numbers and rapid reproduction. The evolutionary journey from microbe to animal, which on Earth took billions of years of relative genetic stability, becomes an impossible climb on a planet where the genetic blueprint is being randomly rewritten by a radioactive storm. Second, and perhaps more insidiously, is the chemical impact on the atmosphere itself. This relentless particle flux does not just damage life, it actively poisons the environment life needs. The intense radiation can fundamentally alter atmospheric chemistry. For a world like Earth, one of the most critical processes involves our protective ozone layer. High in our stratosphere, a delicate blanket of ozone molecules absorbs the sun's most harmful ultraviolet radiation. But the cascade of particles from a severe stellar storm can trigger chemical reactions that break ozone apart, creating temporary but devastating holes in this planetary sunscreen. Without it, lethal UV rays flood the surface, sterilizing land and shallow seas. On a planet orbiting an active star, these ozone destruction events would not be rare. They could be chronic, preventing the layer from ever properly forming. Furthermore, the particle bombardment can force atmospheric gases into new, undesirable combinations. It could break down benign molecules and recombine them into potent greenhouse gases, potentially triggering a runaway heating effect even on a world that started in the habitable zone. Or it could generate thick, global photochemical smogs that blot out the sun and plunge the surface into a toxic, perpetual twilight. The Aurora Effect, therefore, is not one threat but a chain reaction. The stellar wind attacks the magnetic shield. The shield's failure or overwhelming allows radiation to ravage the atmosphere. The damaged atmosphere then fails in its duties, blocking UV, regulating climate, and providing a stable chemical environment. What remains is a surface simultaneously cooked by ultraviolet light, scoured by particle radiation, and choked by a corrupted atmosphere. This is the cosmic double-edged sword. The same physical processes that paint ethereal lights in the sky also systematically dismantle the very conditions that allow for anything more complex than a bacterium to ever look up and see them. The path to a silent, sterile world is not always a sudden cataclysm. It can be a slow, beautiful, and chemical death by 1,000 radiant cuts. Our closest stellar neighbor offers a sobering test case for this theory. Just over 4 light-years away, orbiting the red dwarf star Proxima Centauri, is a world known as Proxima Centauri b. On paper, it is a discovery that once sparked immense excitement. It is a rocky planet with a mass similar to Earth's, and it orbits within its star's theoretical habitable zone. This is the world next door, a potential Earth twin right in our cosmic backyard. But the reality revealed by closer observation is a harsh lesson in the Aurora Effect. Proxima Centauri is not a gentle star. It is a flare star, one of the most active in our local galaxy. Observations from telescopes have captured it unleashing superflares with terrifying frequency. In one recorded event, the star's brightness increased by a factor of 1,000 in mere seconds, bathing its entire system in a flash of intense X-ray and ultraviolet radiation. For a planet as close as Proxima b, which orbits 20 times nearer to its star than Earth does to the Sun, such an eruption would be an apocalyptic event. The planet receives a dose of X-ray radiation hundreds of times more intense than Earth does. The stellar wind battering its atmosphere is thousands of times denser. If Proxima b has a magnetic field, it is under a siege our planet has never experienced, not even in its most ancient, violent past. Without a magnetic field, the situation is even more dire. Scientists modeling these interactions paint a grim picture. The auroral displays on Proxima b would not be confined to polar regions. They would be a permanent, planet-wide phenomenon. The entire sky, from pole to pole, would constantly shimmer and pulse with lethal light. This is not the serene green glow of our northern lights. It would be a brilliant, chaotic tapestry of colors, driven by the relentless bombardment of high-energy particles slamming into whatever atmosphere remains. This constant auroral activity is not a sign of planetary health, but of a world in its death throes. It represents the atmosphere being actively torn apart, molecule by molecule, in a process of sputtering and erosion. Any surface water would long since have been lost to space or locked away as ice on a perpetually dark side. The surface itself would be bathed in radiation levels that would shatter complex organic molecules and make the preservation of genetic information over geological timescales a virtual impossibility. Proxima Centauri b, our nearest exoplanet hope, likely stands as a stark monument to the Aurora Effect. It is a world that meets the most basic criterion for life. It is rocky and in the zone but fails every other test of a stable, nurturing home. It is a planet-sized laboratory demonstrating how a beautiful, dancing sky can be the signature of a sterile, radioactive wasteland. Proxima Centauri b's likely fate forces a startling reappraisal of our own star. We orbit a remarkably stable furnace. Our Sun is classified as a G-type main sequence star, a yellow dwarf which places it in a minority among the galaxy's stellar population. It follows a predictable, roughly 11-year cycle of activity where sunspot numbers rise and fall. During solar maximum, we do experience increased solar flares and coronal mass ejections. But even at its most tempestuous, our Sun is a placid pond compared to the raging ocean of a young red dwarf. To understand the scale, we can look back to a historical event that serves as our benchmark for severe space weather. In September 1859, a colossal solar storm, now called the Carrington Event, struck Earth. A coronal mass ejection of unprecedented power raced from the Sun and about 17 hours later slammed into our magnetosphere. The resulting geomagnetic storm was so powerful that brilliant auroras were seen as far south as the Caribbean. Telegraph systems, the high-tech communication networks of the era, failed spectacularly. Operators reported sparks flying from equipment, papers catching fire, and being able to send messages even with their batteries disconnected, powered solely by the currents induced in the wires by the storm. It was a global technological disruption, a preview of the vulnerability of our modern electrical grid to such an event. Yet for all its legendary power, the Carrington Event was a single, exceptional outburst. Its biological impact on Earth was negligible. Our atmosphere and magnetic field absorbed the blow, protecting every living thing on the surface. Now contrast that with the environment of a planet like Proxima b. What was for us a once in a century or even once in a millennium catastrophe is for them a Tuesday. The superflares that regularly erupt from Proxima Centauri can be dozens of times more energetic than the Carrington Event. And they do not come alone or rarely. They are a constant drumbeat barrage. Our Sun's relative calm is not a trivial detail. It is the foundation upon which billions of years of uninterrupted evolutionary progress were built. It allowed Earth's magnetic field and atmosphere to operate as a stable, long-term shield, not an overwhelmed and failing barrier. This moderate behavior provided the consistent, low-radiation environment necessary for DNA to replicate with fidelity, for complex multicellular organisms to develop intricate systems, and for intelligence to eventually emerge. The Sun's stability granted us the most precious resource of all, a deep, geological time without a global reset. In a galaxy where stellar fury may be the norm, our gentle G-type star appears not just as our home star, but as a rare and benevolent guardian. That multi-billion-year journey from microbe to mammal required something extraordinary on Earth, deep, uninterrupted time. Evolution is not a sprint. It is an achingly slow marathon of trial and error, of incremental changes accumulating over countless generations. The leap from single-celled life to the first complex organisms took nearly 2 billion years. The path from those early multicellular creatures to the first animals took hundreds of millions more. Each of these monumental transitions required stable environments that persisted for geological epochs, allowing for genetic experiments to play out without the entire game board being wiped clean. This is the silent, non-negotiable demand of complex life, planetary stability measured in hundreds of millions of years. The Aurora Effect directly attacks this requirement. It installs a cosmic reset button on a planet's biosphere, and it presses that button not once but repeatedly. Imagine a world where every few thousand years a cataclysmic stellar flare strikes. The sky erupts in lethal radiation, the atmosphere is chemically scarred, and the surface is sterilized down to a depth of several feet. Any complex life that had begun to gain a foothold is eradicated. The survivors are the simplest, hardiest microbes, buried deep in rock or huddled around hydrothermal vents on the ocean floor. Life persists, but it is forced back to square one. It must begin the long climb toward complexity all over again, only to be struck down by the next flare before it can get very far. This creates a brutal evolutionary treadmill. Life is stuck in a perpetual state of recovery, never granted the long, peaceful stretches necessary for innovation. It is a race against time where the clock is constantly being smashed. You cannot build a cathedral if a hurricane knocks down your foundation every decade. Similarly, you cannot evolve a nervous system, a circulatory system, or a brain if your planet's environment is being violently rebooted on a timescale far shorter than the development of those features requires. The window for intelligence to emerge may only open if the planetary conditions remain benign for a continuous span of time that is, by cosmic standards, almost unthinkably long. For a world orbiting a tempestuous star, that window may never open at all. The silence we hear may not be the silence of dead civilizations, but the silence of worlds where the starting gun for the race of life keeps firing over and over, with no runner ever allowed to leave the blocks. This resilience is written into the very bedrock of our planet. In the darkest depths of our oceans, around scalding hydrothermal vents that spew toxic chemicals, entire ecosystems thrive without sunlight. In the bone-dry valleys of Antarctica, microbes survive inside porous rocks. In the heart of nuclear reactors and deep underground in radioactive waste sites, we find bacteria that not only endure intense radiation but actually use it. These are Earth's extremophiles, life forms that push the boundaries of what we once thought possible. They are a testament to the raw, stubborn tenacity of life at its most basic. Their existence offers a crucial caveat to the Aurora Effect. It suggests that across the galaxy, simple, single-celled life may be far more common than we dare hope. A world bathed in radiation with a thin or toxic atmosphere might still harbor microbial communities huddled in subsurface aquifers, shielded by miles of rock, or clinging to existence in the perpetual dark of a deep ocean. The universe could, in fact, be teeming with bacteria, but there is a vast, silent chasm between a planet of microbes and a planet with a biosphere we would recognize. The leap from a bacterium to a butterfly, from an archaea to an ape, is not just a step in complexity. It is a fundamental change in the rules of existence. Complex multicellular life is a high-stakes gamble. It requires enormous amounts of energy to build and maintain intricate bodies. It demands stable, predictable environments for long gestation periods and the careful rearing of offspring. Most critically, it depends on delicate, centralized systems like nervous systems and brains, which are exquisitely vulnerable to disruption. A developing brain, whether in a womb or an egg, is a masterpiece of precise chemical and electrical signaling. It is a process that can be catastrophically derailed by a single dose of radiation or a sudden shift in atmospheric chemistry. An extremophile bacterium can shrug off a stellar flare by going dormant for 1,000 years. A pregnant mammal, a nesting bird, or a school of fish cannot. They are locked into biological timelines that cannot be paused. The aurora effect, therefore, may not be a filter for life itself. It may be the specific, brutal filter for complexity. It could be the reason the galaxy is painted in shades of green slime, but remains utterly silent of songs, signals, or civilizations. The cosmic reset button spares the microbes in the basement, but it reliably extinguishes any tender, complex experiment taking place in the rooms above. Our own solar system is a gallery of auroral phenomena, each world telling a different story of magnetic fields and stellar winds. Jupiter presents the most spectacular display in our neighborhood. Its auroras are not just polar lights, they are permanent planet-sized rings of brilliance, each larger than Earth itself, glowing in ultraviolet and X-ray light invisible to our eyes. This incredible show is powered by two immense engines. First, Jupiter possesses the most powerful magnetic field of any planet, a result of its churning interior of metallic hydrogen. This creates a magnetosphere so vast it could contain the Sun. Second, its volcanic moon Io constantly spews sulfur and oxygen into space, which becomes ionized and trapped by Jupiter's magnetic field. This creates a secondary, relentless rain of charged particles onto the planet's poles. The result is an auroral factory of staggering power, a constant, beautiful testament to a magnetic giant at work. Yet for all its fury, these lights pose no threat to life because they are confined to the poles by that immensely strong field, and Jupiter itself is a gas giant with no solid surface to protect. The energy is safely dissipated in its upper cloud decks. Now look to Venus. It presents the opposite extreme. Venus is Earth's near twin in size and mass, but it spins too slowly to generate a global magnetic dynamo. It has no planetary magnetic shield, yet astronomers have detected faint, diffuse auroras there. How is this possible? The solar wind interacts directly with Venus's thick carbon dioxide atmosphere. The charged particles slowly erode the upper layers of the air, creating a weak, induced magnetic field in the ionosphere, a ghost of a shield formed by the attack itself. The auroras on Venus are not concentrated at poles. They are a faint global glow, a sign of the atmosphere itself being slowly stripped away under the relentless pressure of the Sun. These two examples, Jupiter and Venus, bookend a critical spectrum. On one end, a powerful magnetic field funnels immense energy into brilliant but localized displays. On the other, a missing magnetic field allows the stellar wind to smother the entire planet in a faint, lethal embrace. Earth sits precisely in the middle of this spectrum. Our magnetic field is strong enough to deflect the bulk of the storm and focus the remainder into safe polar channels, but not so weak that the bombardment becomes global. This is the delicate balance the aurora effect highlights. The presence of an aurora is not the issue. It is the character of that aurora. Is it a contained, beautiful release of energy at the poles, or is it a planet-wide symptom of an atmosphere under siege? The difference between those two states might very well be the difference between a living world and a dead one. The shimmering lights of a distant world could soon be more than a beautiful hypothesis. As a new generation of colossal telescopes prepares to peer into the atmospheres of alien planets, scientists are building a toolkit to read the stories written in their light. For decades, the hunt for life beyond Earth has focused on two main categories of clues. The first are biosignatures, chemical imbalances in a planet's atmosphere that could be produced by living things. Think of oxygen and methane coexisting, a combination that on Earth is maintained by biology. The second are technosignatures, the potential fingerprints of an advanced civilization, like artificial lights on the night side or industrial pollutants in the air. But there is a third, more ominous category now gaining attention, the auroral signature. This is not a sign of life, but a sign of its profound unlikelihood. The idea is both simple and revolutionary. When we finally gather enough light from an exoplanet to split it into a spectrum, a chemical barcode of its atmosphere, we will not just be looking for the lines of water vapor or oxygen. We will also be searching for the specific, telltale emission lines of atoms and molecules that have been violently excited by high-energy particle bombardment. These are the spectral fingerprints of an aurora. On Earth, we see the green glow of oxygen and the reds of nitrogen. On a world orbiting a furious red dwarf, we might detect the intense, unnatural glow of hydrogen or helium, signs of an atmosphere being stripped raw. Detecting such a powerful, global auroral signal would be a monumental discovery, but a deeply sobering one. It would act as a negative biosignature. It would tell us that regardless of how perfectly that planet sits in its star's theoretical habitable zone, its surface is almost certainly a radioactive hellscape. The very phenomenon that makes a world visible to us across the light years, its glowing atmosphere, could be the evidence that condemns it as sterile. This transforms the aurora from a local spectacle into a universal diagnostic tool, a way to take the temperature of a planet's relationship with its star from 100 light-years away. Finding a strong auroral signature would instantly reclassify a promising Earth-sized world from a potential garden to a confirmed aurora factory, saving us decades of hopeful speculation and redirecting the search to quieter, more promising corners of the galaxy. This brings us back to a profound and humbling idea about our place in the cosmos, the rare Earth hypothesis. For years, this argument has suggested that the evolution of complex, intelligent life requires a long and improbable checklist. A large moon to stabilize the planet's tilt, plate tectonics to recycle carbon and regulate climate, the right position in the galactic suburbs away from violent supernova. The list goes on. Each item seems like a lucky break, and together they paint a picture of Earth not as a common template, but as a cosmic fluke. The Aurora Effect doesn't contradict this idea. It supercharges it, adding a terrifying new prerequisite to the list. It argues that before a planet can even worry about having a large moon or active geology, it must first win a brutal and ongoing battle for survival against its own star. This shifts the focus from planetary quirks to stellar temperament. The most common stars are violent. The planets that orbit them are exposed, and a magnetic field strong enough to last billions of years is not a given. It requires a planet of the right size and composition, with a molten, churning core that refuses to cool and die. Think of it as a cosmic obstacle course. A planet must first form in the narrow habitable zone of a star that is, against the galactic odds, remarkably calm. It must be large enough to generate a protective magnetic dynamo, but not so large it becomes a gas giant. It must hold onto a thick atmosphere despite the stellar wind, and it must do all of this while maintaining stable conditions not for 1,000,000 years but for billions. The Aurora Effect highlights that one of the greatest filters may be temporal. It's about endurance. A planet needs to be a safe harbor not just in space but in deep, deep time. Every red dwarf superflare, every coronal mass ejection that washes over a world is a test. Fail that test too often, and the planet is permanently relegated to the realm of microbes or worse, sterility. Our existence, then, relies on a chain of cosmic good fortune so long and fragile it feels miraculous. We orbit a stable star in its prime. Our planet's iron heart still beats strongly after 4.5 billion years, generating that invisible shield. Our atmosphere is deep and resilient. We are not just in the right place, we have the right defenses, and we have maintained them for an almost incomprehensible duration. The silence we hear when we listen to the stars may not be a puzzle. It may be the expected outcome. If the Aurora Effect is correct, then Earth-like worlds with Earth-like biospheres are not just rare. They might be the rarest jewels in the entire galaxy, isolated oases of calm in a universe filled with beautiful, deadly light. Yet for all its compelling logic, the Aurora Effect is not a cosmic death sentence. Science thrives on debate, and a chorus of optimistic voices reminds us that life, in its relentless ingenuity, might find paths we have not yet imagined. They argue that we are thinking like surface-dwelling mammals on a temperate world, projecting our own fragility onto the universe. What if complex life does not need a serene, Earth-like garden to flourish? It could evolve in radically different forms in places we would consider hellish. Deep beneath the icy crust of a moon like Europa, entire ecosystems could thrive in sunless oceans, warmed by tidal forces and shielded from stellar radiation by miles of solid ice. On a planet with a thin atmosphere, life might retreat entirely underground, building vast networks in labyrinthine caves, safe from the radiation scouring the surface. Evolution could even engineer biological solutions to the radiation problem itself. Organisms might develop natural melanin-like shields, incorporate radiation-resistant minerals into their exoskeletons, or possess DNA repair mechanisms so efficient they make ours look primitive. In this view, life is not a delicate flame easily snuffed out, but a tenacious force that adapts to fill any niche, no matter how extreme. Furthermore, the planetary defenses themselves might be more robust than we assume. While tidally locked planets face immense challenges, they are not automatically doomed. A large, iron-rich world orbiting a red dwarf could generate a magnetic field far more powerful than Earth's, a global shield of immense strength capable of standing firm against the stellar tempest. We see a hint of this possibility in our own solar system with Jupiter. Its magnetic field is 20,000 times stronger than Earth's. If a rocky planet in a red dwarf's habitable zone had a dynamo even a fraction of that power, it could create a protective bubble large enough to safeguard its atmosphere and surface. The planet's star-facing side might still be bombarded, but the field could deflect and channel the storm in a way that preserves a habitable zone on the surface, perhaps in the twilight band between day and night. Additionally, a planet could begin its life with an atmosphere so incredibly thick, a super-Earth with a primordial envelope of hydrogen and helium, that even relentless stellar erosion would take billions of years to strip it down to a dangerous level. Beneath such a dense, opaque blanket, the surface might be dark and pressurized, but liquid water could exist, and life could adapt to the strange conditions below. This scientific dialogue is crucial. It prevents us from falling into a trap of cosmic pessimism. The Aurora Effect presents a powerful filter, a likely reason why complex, surface-dwelling life like ours might be exceptionally rare. But it does not and cannot proclaim impossibility. It outlines a probable barrier, not an absolute law. The universe has a habit of surprising us, of revealing solutions more clever than our conjectures. When we search the skies, we must remember we are looking for life as we do not know it. The first sign of an alien biosphere might not be the gentle green of chlorophyll, but the heat signature of a volcanic vent ecosystem on a frozen moon. It might not be an oxygen-rich atmosphere, but the complex chemistry of a shrouded, high-pressure world. The debate itself refines our search, telling us to listen not just in the quiet places, but to look more carefully at the violent ones for signs of resilience we have yet to comprehend. The silence may yet be broken by a form of life that learned to sing in the dark, sheltered not by a gentle sun, but by its own incredible biological or planetary fortitude. The search for alien intelligence now faces a profound strategic choice, guided by the stark logic of the Aurora Effect. For decades, the SETI program, the search for extraterrestrial intelligence, has scanned the heavens listening for a signal, any signal that would break the cosmic silence. Its approach has often been one of broad listening, casting a wide net across the sky in the hope of a lucky catch. But if the hypothesis of a deadly stellar filter holds true, then our entire search strategy may need a fundamental recalibration. It tells us that not all stars are created equal in the quest for complex communicative life. The most promising targets may not be the most common ones. This realization forces a difficult but necessary shift. We must point our most sensitive antennas away from the noisy, flaring neighborhoods of red dwarf stars and instead focus our precious listening time on the quieter, more stable solar analogs. G-type stars like our Sun and their slightly cooler, longer-lived K-type cousins become the prime real estate for a galactic search. These stars are less numerous, making the hunt harder from the start, but they offer the long-term planetary stability that complex biology and technological civilization seem to require. A planet orbiting such a star has a fighting chance to maintain its atmosphere, protect its surface from radiation, and grant its life forms the deep time needed to not just evolve, but to look up, wonder, and eventually build a transmitter. This is a search for needles in a smaller but far more promising haystack. The implications run even deeper than simply choosing which stars to monitor. It reshapes how we interpret the Great Silence itself. For years, the lack of detected signals has been a source of growing unease, a puzzle begging for an answer. The Aurora Effect offers a chillingly simple one. Perhaps we are not hearing anyone because in the vast majority of cases, there is simply no one there to send a signal. The silence is not a sign of civilization's hiding, choosing not to communicate, or having transcended beyond radio waves. It could be the natural background noise of a galaxy where the conditions for technological intelligence almost never coalesce. When we listen to a red dwarf system and hear nothing, we should not be disappointed. We might instead be listening to a confirmation of the theory, a silent, sterile world where any potential for complex life was extinguished by its own star eons ago. This changes the emotional weight of the search. It turns SETI from a hopeful scan for neighbors into a meticulous archaeological dig for the rarest of relics. Every hour spent listening to a calm, sun-like star is an hour spent in the most probable neighborhood for a success that is, by definition, extraordinarily unlikely. It is a testament to human patience and optimism. This refined search also asks new questions of the data we collect. Beyond just listening for an intentional radio beacon, astronomers might now look for indirect signs of a protected, living world. Could we detect the subtle radio emissions from a planet's magnetic field interacting with its star, a sign of that crucial shield? Could future telescopes discern atmospheric chemistry that suggests not just life, but a thick, stable, long-lived biosphere? The search for intelligence becomes intertwined with the search for planetary fortitude. We are not just listening for a message, we are looking for the signature of a safe harbor. This perspective makes the discovery of any signal infinitely more precious. Finding a transmission from a planet orbiting a quiet star would not just tell us we are not alone. It would tell us that another world has run the same incredible gauntlet of cosmic luck and endurance that Earth has. It would mean that against staggering odds, the universe has crafted another island of calm, another refuge where light could give rise to life, and life could give rise to a question sent out across the void. In that potential signal, we would hear an echo of our own improbable story. This line of reasoning inevitably brushes against a deeper philosophical question. If the conditions for our existence are so astronomically improbable, then why are we here to ponder them at all? This puzzle is addressed by something called the anthropic principle. In its simplest form, it states that we can only observe a universe that is compatible with our existence as observers. We are not random cosmic tourists. We are products of this specific cosmos, looking out from within it. When we apply this to the Aurora Effect, its implications become both humbling and clarifying. It means we did not evolve on a typical planet around a typical star. We evolved on a planet that, by a staggering series of cosmic coincidences, orbits an unusually calm star and possesses a set of planetary shields that have remained robust for over 4 billion years. Our very presence here is a form of observational bias. We are the winners reporting from inside the casino, while the silent, sterile worlds represent the countless losing tickets. This perspective reframes our search for life from a mission of finding neighbors to an investigation of our own profound rarity. It suggests that Earth may not be a common template but a cosmic jackpot. The silence we hear when we listen to the stars might not be a mystery waiting to be solved. It could be the default state of a galaxy where the recipe for complex life is written in vanishingly small print. The ingredients: a stable star, a magnetic dynamo, a thick atmosphere, a large moon, plate tectonics, are each uncommon. The instructions requiring them to all persist together in harmony for eons are almost impossible to follow. So when we look up at the quiet, dark sky, we are not looking out at a universe empty of promise. We are looking out at a universe that makes our own quiet corner feel like a miracle. This does not mean we are alone, but it does mean that if others are out there, they too are the winners of their own impossible lottery, sheltered on their own islands of calm in a sea of stellar fury. Our existence may be a data point of one, but it is a data point that proves the improbable is possible. This cosmic filter does not just explain our past. It must also guide our future. If humanity ever dreams of spreading beyond our fragile blue cradle, of building homes on other worlds or even terraforming them, the Aurora Effect becomes a survival manual. Our first instinct might be to aim for the nearest targets, the tempting red dwarf systems like Proxima Centauri with their seemingly abundant rocky planets. That would be a catastrophic mistake. Colonizing a world orbiting a flare star would be like building a wooden village on the slopes of an active volcano because the soil is fertile. The initial appeal masks a fundamental, existential threat. No amount of advanced technology could easily compensate for a star that regularly unleashes sterilizing blasts of radiation. Our habitats would need to be buried under miles of rock, our energy systems hardened against electromagnetic pulses that could fry circuitry globally, and our biology perpetually shielded. It would be a life of permanent siege, not a flourishing new branch of civilization. The lesson is clear. For a sustainable, long-term future among the stars, we must be choosy. We must bypass the noisy, violent neighborhoods and seek out quieter stellar real estate. Our target should be the solar analogs, the stable G-type and K-type stars that mirror our sun's gentle behavior. These stars may be farther away, making the journey longer and more difficult, but they offer the only plausible foundation for a world where life can exist openly on the surface, where agriculture can thrive under an open sky, and where children can look up without fear of a deadly solar flare. The Aurora Effect transforms from a theory about alien life into a practical blueprint for our own survival. It teaches us that the most important feature of a new home isn't just its size or composition, but the temperament of its sun. Our interstellar ambitions must be tempered by cosmic meteorology, choosing calm skies over stormy ones, no matter how distant they may seem. But what if a civilization could build its own cosmic umbrella? The Aurora Effect presents a brutal filter imposed by nature, but it does not account for a single, transformative variable: intelligence itself. A species that survives the gauntlet to reach technological maturity might not remain a passive prisoner of its star's fury. It could become an architect of its own planetary destiny. This is the realm of speculative engineering, where the solutions sound like science fiction but are rooted in known physics. For a civilization advanced enough, perhaps classified as a type Roman II on the Kardashev scale, one capable of harnessing the entire energy output of its star, the challenge of a violent sun might not be an end, but a monumental engineering project. Their first task would be to reinforce the very shield that protected their ancestors. We can envision planet-scale magnetic field generators, colossal superconducting rings buried in the crust or orbiting in space, actively amplifying and stabilizing the planet's natural magnetosphere. These would not be passive defenses, but dynamic systems that could be strengthened in anticipation of a solar superflare, actively pushing back against the stellar wind to maintain a safe bubble. If the atmosphere had been eroded, they might construct atmospheric replenishment factories, mining volatile elements from comets, moons, or the planet's own mantle to slowly rebuild the air they lost over eons. They could even engineer photosynthetic organisms or chemical processes to lock that new atmosphere into a stable, breathable balance. The most staggering concept of all would be an orbital radiation shield. Imagine a vast, thin mesh of superconducting material positioned at the Lagrange point between the planet and its star, a permanent sunshade that filters out lethal X-rays and particle radiation while allowing visible life-giving light to pass through. It would be a technological Dyson swarm not for collecting energy but for ensuring survival, a megastructure that literally terraforms the space between the world and its sun. These are not blueprints but thought experiments that stretch our understanding of what might be possible. They suggest a profound idea: the Great Filter might not be a permanent wall. It could be a door, one that requires a key of unimaginable technological sophistication to unlock. A planet around a violent star might still give rise to intelligent life if that life begins in deep, shielded refuges, perhaps in subsurface oceans or deep cavern networks. Their entire early history would be one of survival in the dark, but upon achieving mastery over matter and energy, they could embark on the ultimate project, turning their entire world into a lifeboat and then a garden. They would not wait for geological chance to provide a magnetic field. They would build one. They would not accept a thin, toxic atmosphere. They would manufacture a new one. Their auroras would not be a symptom of atmospheric decay, but a controlled, artistic display powered by their own orbital defenses. In this scenario, the Aurora Effect becomes not just a filter, but a forge. It creates an environment so relentlessly hostile that any intelligence that emerges from it would, by necessity, be forced to become a master of planetary engineering almost immediately. Their civilization would be born from an endless emergency, giving them a drive and a technological trajectory utterly different from our own. While we enjoyed billions of years of natural peace to develop at a leisurely pace, their ascent would be a desperate, brilliant sprint against extinction. Their first radio signals might not be gentle greetings, but the hum of continent-sized generators holding back the storm. So when we listen to the quiet stars, perhaps we are listening for the wrong thing. We listen for a signal like our own, from a planet like our own. But the first civilization we hear might not come from a tranquil, Earth-like world. It might broadcast from a fortress, a fully engineered planetary ark orbiting a furious red dwarf, its very existence a triumphant declaration that life, once awakened, can sometimes rewire the rules of its own universe. Our planet's safety depends on more than just a quiet star. It depends on living in a quiet neighborhood within an even quieter galaxy. This brings us to a concept that layers another daunting filter on top of all we've discussed: the galactic habitable zone. Imagine the Milky Way not as a uniform disk of stars, but as a cosmic city with distinct districts, each with its own dangers and advantages. The bustling downtown core, the galactic center, is a spectacular but lethal place. It's packed with stars bathing the area in intense radiation. It's also home to a supermassive black hole whose gravitational tantrums can wreak havoc. Most dangerously, the dense stellar crowding means supernova. The catastrophic explosions of dying giant stars are far more frequent there. A nearby supernova is an extinction-level event on a scale that makes solar flares seem trivial. It can bathe entire planetary systems in gamma rays and cosmic rays, stripping atmospheres and sterilizing surfaces in an instant. To foster life that lasts for billions of years, a planet needs to be far from this chaotic, radioactive downtown. It needs to reside in the galactic suburbs, in the quieter spiral arms. This is the galactic habitable zone, a region where star density is low enough to minimize the risk of a deadly nearby supernova, yet high enough that earlier generations of stars have produced and scattered the heavy elements like iron, carbon, and oxygen necessary to form rocky planets and the molecules of life. Earth sits comfortably within this zone, about halfway out from the bustling center, in a relatively calm spiral arm. This positioning granted us another layer of cosmic peace, the deep time stability to evolve without our planet's biosphere being randomly reset by a stellar explosion from a neighboring star. But here is where the filters begin to stack, creating a Russian doll of rarity. The galactic habitable zone gives you a safe street in the cosmic city. It does not guarantee you a safe house. Within this broadly favorable region, you must then find a stellar system with a stable, long-lived star. And as we've learned, most stars are not like our Sun. They are the tempestuous red dwarfs, so you must find one of the minority of calm solar analogues. This is the second filter. Then, orbiting that quiet star, you need a rocky planet of just the right size and composition, positioned perfectly within the star's own habitable zone. A third filter, that planet must have a churning molten core to generate a persistent global magnetic field. A fourth, it must have held onto a thick, robust atmosphere for billions of years. A fifth, it likely needs a large moon to stabilize its axial tilt and climate. A sixth, the list goes on. The Aurora Effect adds a critical, dynamic layer to this local stellar filter. It says that even if a planet checks all the boxes for being Earth-sized and in the zone, its existence as a complex biosphere hinges on the ongoing, violent relationship between its atmosphere and its star's wind. A planet in the galactic suburbs orbiting a calm star could still be rendered sterile if it lacks that magnetic shield or if its atmosphere is too thin. The habitable conditions are not a permanent state, but a fragile balance that must be maintained against a constant cosmic pressure. So truly habitable worlds are not just rare finds in a vast galaxy. They are nested rarities within rarities. They must exist in the right part of the galaxy, around the right kind of star, and possess the right planetary defenses, all sustained for an almost impossibly long duration. Each of these requirements dramatically narrows the field. The silence we perceive when we look at the star-dense core of our galaxy isn't surprising. It's likely a zone of perpetual sterilization. But the deeper, more profound silence may be in the spiral arms themselves, where countless red dwarfs host planets that, while safe from supernova, are being slowly cooked and stripped by their own small, angry suns. Our Earth, then, is not merely a lucky planet. It is a statistical outlier on multiple, independent axes all at once. We reside in the galactic sweet spot around a stellar sweet spot with planetary defenses that have proven sweetly durable. This layered filtering suggests that if complex, communicative life exists elsewhere, it is not spread like a thin film across the galaxy. It will be isolated in extraordinarily specific pockets, separated by vast deserts of sterile worlds and microbial slime. The distances between these oases wouldn't just be measured in light years of empty space, but in light years of fundamentally hostile stellar systems that never could have fostered such life in the first place. The cosmic city might have billions of houses, but only a handful have the right foundation, the right roof, and have never been hit by a meteor, a flood, or a fire. We live in one of those miraculous, sheltered homes, looking out at a neighborhood that, for all its glittering stars, may be filled with buildings that are dark, empty, or crumbling. The story of cosmic filters is not just a tale of distant stars. It is a mirror reflecting a crisis unfolding right here at home. Our planet is currently undergoing a massive, unplanned experiment in planetary alteration, one we have authored ourselves. Human-driven climate change is, in a profound sense, a terrestrial version of the Aurora Effect. It is a rapid, violent stress test on the delicate systems that have kept Earth stable for eons. The threat is not a barrage of charged particles from a hostile sun, but a flood of greenhouse gases from our industries, our engines, and our agriculture. Yet the principle is eerily similar. We are actively changing the fundamental chemistry of our atmosphere, weakening its ability to regulate temperature and protect the surface. We are not being attacked from the outside. We are dismantling our own shields from within. the beautiful, complex balance of our biosphere, the very balance that allowed us to evolve, is proving to be terrifyingly fragile. Whether the destabilizing force is a stellar flare or a smokestack, the lesson is the same. A planet's habitability is not a guaranteed state. It is a dynamic, hard-won condition that must be maintained. The Aurora Effect teaches us that a magnetic field and a thick atmosphere are not geological decorations. They are life support systems. Our current crisis makes that abstract lesson viscerally real. We are watching, in real time, what happens when a planet's atmospheric balance is pushed out of equilibrium. We see the symptoms not as beautiful auroras, but as devastating wildfires, intensifying hurricanes, and melting ice caps. The parallel is a chilling wake-up call. For billions of years, Earth's defenses held firm against cosmic storms. Now, in a geological instant, we are proving that those same defenses can be undone from the inside. This transforms our understanding of planetary stewardship. Protecting our magnetic field is beyond our current technology, but safeguarding our atmosphere is not. The fight against climate change is no longer just an environmental or political issue. Framed by the cosmic reality of the Aurora Effect, it becomes a fundamental act of planetary maintenance. It is the work of ensuring our world remains one of those rare protected oases, a calm harbor in the galactic storm. Our survival as a technological civilization may ultimately depend less on whether we find other life in the cosmos, and more on whether we can preserve the miraculous, fragile world that allowed our life to begin. The ultimate test for this idea is not more theory, but more light. We are on the cusp of gathering that evidence with a new generation of observatories designed to see what was once invisible. The James Webb Space Telescope, already revolutionizing our view of the cosmos, is our first true atmospheric analyzer for distant worlds. It does not see planets as points of light, but as complex chemical signatures. When a planet passes in front of its star, a tiny fraction of the starlight filters through that world's atmosphere. Webb's exquisite instruments can split that faint hint of light into a detailed barcode, revealing the fingerprints of molecules like water vapor, carbon dioxide, and methane. But scientists are now training its gaze to look for something else entirely, the spectral signs of a world under siege. They will search for the unnatural glow of atoms excited by constant particle bombardment, or for chemical imbalances that suggest an atmosphere being actively stripped and irradiated. A detection of powerful, global auroral emissions from a rocky world in a habitable zone would be a landmark finding, a strong negative indicator for complex life as we know it. This is just the beginning. On the drawing board for the next decade is an even more ambitious project, the Habitable Worlds Observatory. Conceived as a direct successor to Hubble and Webb, this space telescope will be designed with one primary goal: to directly image and analyze Earth-like planets around Sun-like stars. It would use a sophisticated starshade, a giant sunflower-shaped disk flying in formation thousands of miles away, to block the blinding glare of a star and reveal the faint, pale blue dot of its orbiting world. For the first time, we could get a spectrum of a true Earth analog, not just a world in the habitable zone of a red dwarf. Does it show signs of a thick, stable atmosphere rich in oxygen and water? Or does its light tell a story of atmospheric erosion and high-energy radiation? The Habitable Worlds Observatory could move us from studying probable aurora factories to investigating the only places where complex life is likely to exist, planets around quiet stars. Meanwhile, back on Earth, a different kind of listening is underway. Radio telescopes across the globe are being used not to search for alien signals, but to monitor the tantrums of nearby stars. By tracking the radio bursts from stellar flares on stars like Proxima Centauri, astronomers can measure their frequency and ferocity in real time. This data feeds directly into models of atmospheric erosion, telling us exactly how much punishment a planet's defenses must withstand. Every crackling pop and burst from a distant sun refines our understanding of the stellar environment, helping us predict which exoplanet atmospheres are likely surviving and which are slowly vanishing into the void. Within the next 10 to 15 years, this converging wave of data from Webb, from new radio surveys, and eventually from the Habitable Worlds Observatory will transform the Aurora Effect from a compelling hypothesis into a tested theory. We will no longer have to guess. We will have a growing catalogue of worlds, some showing the vibrant chemistry of stability, and others displaying the stark signature of a beautiful, lethal sky. This is not a distant dream of far future science. The tools are here or being built now. The great silence of the universe may soon be broken not by a radio message, but by the silent, screaming light of 1,000 alien atmospheres, each telling us its own story of cosmic shelter or cosmic storm. The quiet we perceive when we listen to the stars might not be empty at all. It could be the quiet of a nursery where almost every infant is stillborn. The Aurora Effect weaves all these cosmic threads into a single, startling tapestry. It points to a potential great filter, but one that is not a singular event lost in the ancient past or a looming catastrophe in our future. Instead, it is a continuous, grinding process happening right now across billions of worlds. This filter operates in the vast gulf between the spark of simple life and the flowering of complex, intelligent civilization. It is the relentless pressure of a star upon its planets, a daily test of planetary endurance. Imagine the universe not as a place where civilizations rise and fall, but as one where they almost never get to rise in the first place. The galaxy could be a verdant garden of bacteria, with microbial life clinging to existence in underground aquifers and deep-sea vents on countless worlds. But on the surface, where complex organisms need light and air and stability, the conditions are perpetually hostile. The beautiful, shimmering auroras that dance across those skies are not a sign of planetary health. They are the glow of the filter itself at work, a luminous symptom of atmospheric erosion and surface sterilization. This explains the Fermi Paradox with a devastating simplicity. We are not hearing from other civilizations because there are virtually no other civilizations to hear from. The great silence is not a puzzle. It is the expected background noise of a galaxy where the recipe for a technological species requires a list of ingredients so long and a cooking time so undisturbed that the final dish is almost never prepared. The filter is not behind us or ahead of us. For most life-bearing worlds, it is the constant, inescapable present, a permanent state of siege that prevents the story from ever moving to its next chapter. Our story is the breathtaking exception, not the rule. Our journey began with a simple, beautiful sight, the shimmering curtains of light in our own polar skies. We followed that light outward across the void and discovered it might be a cosmic warning sign. The same physics that paints our sky with wonder could, on countless other worlds, be a brush that paints them sterile. We have traveled from the protective embrace of Earth's magnetic field to the violent tantrums of red dwarf stars, from the slow suffocation of Mars to the likely hellscape of Proxima Centauri b. The story of the Aurora Effect is a story of filters. It tells us that liquid water is just the opening line in a much longer, more demanding recipe for complex life. The right star, stable and calm, is not a luxury. It is a necessity. The right planetary shields, a churning magnetic heart and a deep, resilient atmosphere are not optional features. They are the fortress walls that must hold for billions of years. This realization reframes our entire existence. We are not living on a typical planet around a typical star. We are living on a cosmic jackpot ticket, a world that has passed a series of brutal, ongoing tests that most others fail. Our sun is a quiet guardian. Our planet's core still beats strongly after 4.5 billion years. Our atmosphere is a thick, protective blanket. Every one of these conditions is rare on its own. Their convergence here, sustained across eons, is nothing short of miraculous. We are the beneficiaries of a chain of cosmic luck so long and fragile it defies belief. When you look up at the night sky, you are not looking out at a universe teeming with neighbors just like us. You are looking out at a vast, beautiful, and often violent cosmos where islands of calm like ours are the rarest of jewels. The silence we hear is not mysterious. It is the expected background hum of a galaxy where the conditions for a creature to look up and wonder are almost never met. This knowledge comes with a profound responsibility. If our world is such a rare and fragile oasis, then its care is the most important project we will ever undertake. Safeguarding our atmosphere, our climate, and our biosphere is not just environmentalism. It is planetary maintenance. It is the work of ensuring this one improbable haven remains a sanctuary for all the complexity it has nurtured. So tonight, or any night you can, step outside, look up at the stars, find that quiet, yellowish point of light that is our sun, and know that its gentle nature, combined with our planet's enduring fortitude, granted us this chance to be here to think, to feel, and to search. We may yet discover we are not alone, but if we do, those others will be miracles too, singing across the void from their own impossible islands of calm. Until then, the greatest story we know is the one unfolding right here on this precious, shielded world beneath a quiet star. What do you think? Does the Aurora Effect explain the great silence? Share your thoughts below, and as always, thank you for exploring the cosmos with us.